The exploration of cosmic movements, particularly the phenomenon known as dark flow, reveals fascinating insights into the structure and behavior of the universe. Dark flow refers to the unexpected motion of galaxy clusters, which appear to be moving in a specific direction, seemingly influenced by something beyond the observable universe. This mysterious flow was first noted in a study conducted by a team led by Alexander Kashlinsky, who observed that several galaxy clusters were moving toward a specific point in the sky, suggesting a gravitational pull from unseen forces or structures. This observation raises questions about the nature of the universe, particularly regarding the distribution of mass on a cosmic scale, and challenges our understanding of dark matter and dark energy, which comprise much of the universe's mass energy content. The existence of dark flow has led to intense scrutiny, with scientists seeking to understand its implications. Some researchers speculate that dark flow may be linked to superclusters or large-scale structures that extend beyond the observable universe. This idea suggests that there could be vast regions of mass that we cannot currently detect, possibly due to limitations in our observational technology, or because they lie beyond the cosmic horizon. Such discoveries could revolutionize our understanding of cosmic structure and expansion, potentially providing clues about the overall shape and fate of the universe. The study of dark flow also intersects with the investigation of cosmic microwave background radiation, which is the afterglow of the Big Bang. Variations in this radiation can give scientists insights into the distribution of matter in the universe, and when combined with findings related to dark flow, they contribute to a more comprehensive picture of cosmic evolution. By examining the minute temperature fluctuations in the cosmic microwave background, researchers can infer the presence of large-scale structures and how they influence cosmic movements. This connection highlights the intricate web of phenomena that shape our universe. As scientists delve deeper into the mysteries of dark flow, they utilize advanced technologies and methodologies, such as the use of large-scale galaxy surveys and simulations. These tools allow researchers to map the distribution of galaxies and their motions more effectively, revealing patterns that were previously obscured. Through these efforts, the scientific community hopes to unravel the complexities of dark flow and its relationship with fundamental cosmological theories, such as the inflationary model and the nature of dark energy. Another angle of investigation focuses on the potential impact of dark flow on the expansion rate of the universe. The Hubble constant, which measures the rate of expansion, could be influenced by unseen structures pulling galaxy clusters in specific directions. If dark flow continues to be confirmed, dark flow, an intriguing phenomenon in the realm of cosmology, refers to the unusual motion of galaxy clusters, which seem to be moving in a particular direction, away from the expected distribution of cosmic structures. Observations made by the Wilkinson Microwave Anisotropy Probe, or WMAP, have suggested that these galaxy clusters are not just drifting randomly as one might expect from the uniform expansion of the universe, but rather they exhibit a coherent motion towards a specific, particularly towards the constellation Centaurus. This unexpected alignment has stirred considerable interest among astronomers and physicists alike, raising questions about what might be influencing this behavior. One hypothesis suggests that the movement could be caused by gravitational effects from structures outside our observable universe, leading to speculation about the existence of vast, unseen entities or even entire regions of the cosmos that we have yet to comprehend. As scientists dive deeper into this mystery, they are faced with the challenge of distinguishing between what is purely an observational anomaly and what might actually be a sign of something more profound at work. While traditional theories of cosmic expansion derived from the Big Bang model would suggest that galaxy clusters should be uniformly distributed, the presence of dark flow raises the possibility of large scale structures such as superclusters exerting a gravitational pull on these clusters, which might be influencing their trajectories. This idea has opened up discussions about the potential existence of a multiverse, where our universe might be just one of many, each with its own unique characteristics and gravitational influences. Furthermore, the implications of dark flow extend beyond just galaxy movement. They challenge our current understanding of the cosmos, prompting researchers to reconsider the fundamental laws of physics as they apply to large-scale structures. As scientists gather more data, using advanced telescopes and observational technologies, they aim to further explore the characteristics of dark flow, hoping to uncover its origins and the possible forces at play. The idea that we might be witnessing a phenomenon that defies our conventional understanding of cosmic expansion sparks curiosity and excitement within the scientific community, as it suggests that there could be more to the universe than we have yet discovered. This exploration into dark flow embodies the spirit of scientific inquiry as researchers strive to peel back the layers of cosmic mystery, seeking answers to questions that probe the very nature of reality itself. The possibility that our universe is not entirely isolated, but rather influenced by forces beyond our perception, invites deeper examination of the fabric of space and time. As studies continue, the quest to understand dark flow is a fascinating concept in cosmology, referring to the peculiar motion of galaxy clusters that seems to be moving in a specific direction, beyond what can be explained by the gravitational pull of nearby matter. This phenomenon was first suggested by researchers in 2008, who observed that certain galaxy clusters, particularly in the direction of the constellation Centaurus, were moving towards a particular region of the sky which appeared to be an anomaly when compared to the expected distribution of cosmic microwave background radiation, or CMB. The idea that there might be something out there, something that we cannot see, influencing the motion of these galaxies, really challenges our understanding of the universe. The term dark flow suggests that this motion is linked to some unseen forces or structures, possibly related to areas of space that are beyond the observable universe. As we know, our universe is vast and continuously expanding. And while we can observe a lot of it, there are still regions that remain hidden from us due to the finite speed of light and the expansion of space itself. Some scientists hypothesize that dark flow may indicate the influence of superclusters of galaxies, or even other universes, or perhaps the gravitational effects from structures that lie outside our observable horizon. This could be indicative of a larger cosmic structure, suggesting that our universe might not be isolated, but rather part of a greater cosmic web, with influences from regions we cannot directly observe. The implications of dark flow are significant, raising questions about the nature of dark energy and dark matter, which are already enigmatic components of our universe. Dark energy, for instance, is the mysterious force driving the accelerated expansion of the universe, while dark matter, which makes up a substantial portion of the total mass in the cosmos, interacts with visible matter through gravity, yet eludes direct detection. If dark flow is indeed a real phenomenon, it could provide clues about the distribution of dark matter on a larger scale, and how it interacts with the observable universe, adding to the complexity of our cosmic understanding. The evidence for dark flow is still under debate, as some researchers have pointed out that the observations could be affected by local gravitational influences or biases in the data collection methods. However, the discussions surrounding dark flow continue to stimulate interest among astronomers and physicists, leading to new research and observations aimed at uncovering the truth behind this cosmic riddle. As we delve deeper into the universe, utilizing advanced technology like powerful telescopes and sophisticated computer simulations, we may one day unravel the phenomenon of dark flow was first observed in the early 2000s during a study that aimed to understand the large-scale motion of galaxy clusters in the universe, particularly those in the vicinity of the cosmic microwave background, which is the afterglow of the Big Bang, and it provides a snapshot of the early universe. Researchers, led by a team from the University of California, Los Angeles, were analyzing data from the Wilkinson Microwave Anisotropy Probe, ORWAP, which was launched to measure temperature fluctuations in the cosmic microwave background. During their investigation, they noted an unexpected movement of certain galaxy clusters, which seemed to be heading in a specific direction, away from the rest of the universe, rather than moving randomly or being influenced solely by the known gravitational forces of nearby matter. The initial findings indicated that a group of galaxy clusters, particularly those in a region called the Centaurus cluster, exhibited a peculiar velocity that was not fully accounted for by the known gravitational effects of visible matter. This discovery suggested that these clusters were moving towards a mysterious, massive structure, or possibly a concentration of dark matter located far beyond our observable universe. This peculiar motion appeared to be consistent across different galaxy clusters, hinting at a large-scale flow of galaxies that was not explained by the known gravitational forces acting upon them. This led researchers to consider the possibility that there might be structures or phenomena outside of the observable universe exerting gravitational influence on these clusters. The term dark flow was coined to describe this phenomenon, as it implied a movement that was not linked to the known matter and energy in the universe, thus remaining largely hidden or dark. Subsequent studies have aimed to confirm these initial observations and to better understand the implications of dark flow, with some scientists speculating that it could point towards the existence of other universes, or regions beyond our observable universe, which may have different properties. As scientists continued to analyze more data, they found that the flow appeared to be not just a local effect, but rather a large-scale motion affecting clusters over vast cosmic distances. This raised intriguing questions about the overall structure of the universe, as well as its expansion, leading to debates within the cosmological community about the nature and origin of dark flow. Some researchers proposed that dark flow might be evidence of gravitational pull from massive structures that lie outside the observable universe, while others suggested alternative explanations, such as the effects of... In addition to understand dark flow in the universe, scientists utilized a variety of measurements and data that were crucial in revealing this intriguing phenomenon. One of the primary methods involved the analysis of the cosmic microwave background, or COMB, which is the afterglow radiation from the Big Bang. This radiation provides a snapshot of the universe when it was just about 380,000 years old, allowing researchers to study its large scale. By examining the temperature fluctuations in the COMB across different regions of the sky, scientists could infer the gravitational influences from massive structures, such as galaxy clusters, that might be exerting a pull on the flow of galaxies. Additionally, astronomers employed redshift data, which measures how light from distant galaxies shifts towards the red end of the spectrum as they move away from us. This redshift helps in determining the velocity of these galaxies. When scientists observe the velocities of galaxies in certain regions of the universe, they noticed that some were moving in a specific direction, suggesting a coordinated motion that was not fully understood. This led to the hypothesis of dark flow, where galaxies seem to be moving towards a particular area of the sky, seemingly influenced by something beyond the observable universe. Moreover, researchers analyzed the distribution of galaxy clusters, especially in areas known as superclusters. The gravitational pull from these massive clusters can affect the motion of surrounding galaxies. Through simulations and modeling, they compared the observed motions of galaxies with what would be expected based on the distribution of matter in the universe, leading to the identification of anomalies that hinted at dark flow. One of the significant studies that brought dark flow to light was conducted using data from NASA's Wilkinson Microwave Anisotropy Probe, or MAP, which mapped the COMB with high precision. The analysis of this data, combined with other surveys from space telescopes and ground-based observatories, helped to identify patterns in galaxy movements that suggested a collective flow towards a region in the southern hemisphere of the sky. To quantify dark flow, scientists utilize statistical methods to analyze the motion of thousands of galaxies, focusing particularly on the peculiar velocities of galaxies relative to the expected velocities based on the universe's expansion. By correlating these velocities with the large-scale structure of the universe, researchers were able to identify an unusual bulk motion that could not be explained by known forces or structures, leading to the conclusion that there might be unseen influences at play, possibly connected to vast structures beyond the observable universe, such as superclusters or even dark flow, is an intriguing phenomenon in cosmology, differing significantly from other cosmic movements, like dark matter and dark energy, each of which has its own unique characteristics and implications of the universe. To begin with, dark matter, which makes up about 20/7 of the universe, is a type of matter that does not emit, absorb, or reflect light, making it invisible and detectable only through its gravitational effects on visible matter such as stars. And dark matter is believed to play a crucial role in the formation of large-scale structures in the universe, influencing the motion of galaxies and galaxy clusters through its gravitational pull. On the other hand, dark energy, which constitutes roughly 68% of the universe, is a mysterious force causing the accelerated expansion of the universe. While dark matter works to pull things together, dark energy pushes them apart, leading to a cosmic balance that shapes the large-scale structure and evolution of the cosmos. Now, dark flow, in contrast, refers to a peculiar motion observed in galaxy clusters, where they seem to be moving in a specific direction at high speeds, seemingly influenced by structures beyond the observable universe. This phenomenon was first suggested in 2008, when researchers detected that certain galaxy clusters are moving toward a particular region of the sky, which appears to be a gravitational pull from a vast mass, possibly linked to superclusters or even structures that lie outside the observable universe. Unlike dark matter, universe, hinting at the influence of unseen mass on cosmic scales. The existence of dark flow poses questions about the uniformity of the universe, as it suggests that there may be large-scale structures or gravitational influences that we have yet to fully understand, which could potentially reshape our models of the cosmos. This movement is not consistent with what we expect from the isotropic and homogeneous universe described by the standard cosmological model, which assumes that, on large scales, the universe looks the same in all directions. Therefore, dark flow challenges this notion, making scientists consider the possibility of new physics or previously unknown massive structures lurking at the edges of our observable universe. In summary, while dark matter and dark energy are essential components influencing the fabric of the universe, dark flow represents the directional movement of galaxy clusters, hinting at the influence of unseen dark flow. A term that might sound mysterious refers to a peculiar galaxy clusters suggesting they are moving in a specific direction, away from the rest of the universe, in a way that doesn't seem to align with the expected cosmic expansion. This observation, first made by researchers analyzing the cosmic microwave background radiation, raises fascinating questions about the universe's structure, potentially hinting at influences beyond the observable universe. If dark flow is indeed a real phenomenon, it could imply that our universe is not an isolated system, but rather part of a larger cosmic structure, possibly influenced by regions of space that we cannot see, or even by other universes. If the multiverse, such a revelation would challenge our current understanding of cosmic evolution, suggesting that gravitational forces from unseen areas could be influencing the motion of visible matter, which is a concept that could revolutionize our grasp of cosmic dynamics. Moreover, dark flow could also lead to a re-evaluation of the standard model of cosmology, particularly in how we understand the distribution of dark matter and dark energy. If the motion of galaxy clusters is being driven by factors we haven't yet identified, it could indicate that our current models are missing crucial elements, perhaps even new physics that we have yet to discover. This might prompt scientists to develop new theories or modify existing ones to account for these unexpected movements, thereby deepening our understanding of gravitational interactions on a grand scale. Additionally, the implications of dark flow extend to the study of large-scale structures in the universe, such as filaments and voids, which are integral to the cosmic web. Observing how galaxy clusters interact with these structures could provide insights into the history of the universe, including how galaxies formed and evolved over billions of years. If dark flow is confirmed, it could help astronomers piece together a more comprehensive picture of the universe's layout, revealing how different regions of space are interconnected and how they influence each other through gravitational forces. Furthermore, the existence of dark flow might encourage advancements in observational technology and techniques. To further investigate this phenomenon, astronomers may develop more sensitive instruments capable of detecting subtle motions and variations in distant galaxy clusters, which could reveal new aspects of cosmic behavior. This could lead to a cascade of discoveries about the universe, pushing the boundaries of what we know about the cosmos. In a broader sense, understanding dark flow could provoke philosophical discussions about our place in the universe. If we are indeed part of a larger structure, what observational evidence in astronomy plays a crucial role in our understanding of the universe, as it helps scientists gather data about celestial objects and phenomena, often using telescopes and other instruments to capture information that is light years away from us. This evidence is foundational, providing a means to support or refute theories about the cosmos. One of the most compelling examples of observational evidence is the discovery of the cosmic microwave background. Evidence is the study of distant galaxies, particularly their redshift, which is a phenomenon that occurs when the light from an object is stretched as it moves away from us, indicating that the universe is expanding. Edwin Hubble, in The 1920s observed this redshift in light from various galaxies, leading to the formulation of Hubble's law, which describes the relationship between the distance of galaxies and their recessional velocity. This observation has profound implications, suggesting that the universe, starting from a singularity, has been growing for billions of years, and it raises interesting questions about the ultimate fate of the cosmos. In addition, the discovery of exoplanets, or planets outside our solar system, has been an exciting area of observational evidence in recent years. Methods such as the transit method, in which a planet passes in front of its host star, causing a slight dimming of the star's light. Astronomers, to identify these distant worlds, the Kepler Space Telescope, launched in 2009, has been particularly successful in this endeavor, identifying thousands of potential exoplanets, which opens up discussion about the possibility of life elsewhere in the universe, as we consider the conditions that might allow life to flourish on these distant planets. Moreover, the study of gravitational waves, which were first detected in 2015 by the LIGO Observatory, has provided a new way to observe astronomical events. These ripples in space-time caused by massive objects like merging black holes or neutron stars offer insights into some of the universe's most violent occurrences, further deepening our understanding of gravity, and the concept of dark flow emerged from intriguing observations made by astronomers. Studying the motion of galaxy clusters, particularly those in the vicinity of the cosmic microwave background radiation, which is the afterglow of the Big Bang. Researchers, while analyzing the movement of these galaxy clusters, noticed something unusual. Most galaxies and galaxy clusters in the universe tend to move in a random fashion, influenced by the gravitational pull of nearby matter. However, a subset of these clusters, specifically those in the direction of the constellation Centaurus, appeared to be moving in a coherent manner, in a direction that did not seem to align with the known large-scale structure of the universe. This peculiar motion suggested that these galaxy clusters were being pulled by an unseen force, which was later dubbed dark flow. The initial observations that sparked interest in this phenomenon were made using data from NASA's Wilkinson Microwave Anisotropy probe, or MAP, which mapped the temperature, fluctuations in the cosmic microwave background radiation. These fluctuations provide a snapshot of the universe's early moments, and the data revealed that certain galaxy clusters were not just moving randomly, but rather were showing a significant velocity toward a specific region of the sky, which raised questions about what could possibly be exerting such a force. Further investigations showed that this movement was not isolated. It seemed to be a systematic flow that affected multiple galaxy clusters, indicating that there was something large and massive, beyond the observable universe, exerting influence. The researchers found that this movement could not be explained solely by the gravitational effects of known structures, like galaxies and dark matter, suggesting that there might be a significant amount of unseen mass or energy, perhaps from regions of space that are beyond our observable limits. This led to speculations about the existence of a vast superstructure, potentially lying outside the observable universe, which could be a remnant from the early universe's formation, influencing the motion of these galaxy clusters. Some scientists have even proposed that this could be an indication of an entirely different universe or a region of space that is not bound by the same physical laws we understand. The idea of dark flow challenges our understanding of cosmology and raises fundamental questions about the universe's structure and the nature of dark energy and dark matter. The studies on dark flow have stimulated significant discussions in the scientific community, leading to further observations and analyses. Researchers have used different telescopes and observational techniques to gather more data, aiming to confirm the existence of this phenomenon. However, it remains a topic of the cosmic microwave background, often abbreviated as COM, is a fascinating remnant from the early universe, a relic of the Big Bang which fills the universe with a faint glow, almost like an echo of its fiery birth. When scientists measure the COM, they are essentially looking at the afterglow of the hot, dense state of the universe, which cooled down as it expanded. This background radiation is remarkably uniform, but it does have tiny fluctuations, which are crucial for understanding the large-scale structure of the universe, and these fluctuations can provide insights into various cosmic phenomena, including something intriguing known as dark flow. Dark flow refers to the peculiar motion of galaxy clusters, which seem to be moving in a specific direction, contrary to what one might expect from the isotropic expansion of the universe. Observations of the COM have revealed that, while most of the universe appears homogeneous on large scales, there are regions where this uniformity breaks down, leading to the idea that some gravitational influences might be acting on these galaxy clusters, pulling them in a particular direction. The COM measurements, especially those from the Wilkinson Microwave Anisotropy Probe, or MUP, have provided a wealth of data about the temperature fluctuations in the COM, which helps researchers map out the distribution of matter and energy in the universe. These maps have shown that certain galaxy clusters are moving towards a region in the sky known as the cold spot, which is an area of lower temperature in the COM. This cold spot has sparked interest because if the clusters are moving towards it, it suggests that there might be some large-scale structures beyond the observable universe, affecting their motion, possibly hinting at the existence of unseen mass or energy, which could be related to. The idea is that the movements of these galaxy clusters, as indicated by the COM measurements, imply that there are gravitational forces at play, pulling them towards a region that we cannot see, which might be associated with superclusters or even other universes, given the mysteries surrounding dark flow. Furthermore, researchers have also pointed out that the alignment of these galaxy clusters with the COM anomalies could indicate that there are underlying structures that we are not yet aware of, possibly linked to dark energy or other cosmic phenomena that challenge our current understanding of the universe. In conclusion, the connection between COM measurements and the concept of dark flow underscores the complexity of the universe and highlights the ongoing journey of scientific exploration as astronomers' galaxy clusters, which are massive groups of galaxies bound together by gravity, play a crucial role in our understanding of dark flow, a phenomenon that suggests the existence of large-scale cosmic motion in the universe. Dark flow refers to the observed motion of galaxy clusters that seems to be directed towards a specific region of the sky, defying the expectations set by the standard model of cosmology, which assumes that the universe is homogeneous and isotropic at large scales. When astronomers study these clusters, they can detect how they move relative to the cosmic microwave background radiation, which is the afterglow of the Big Bang. And this can reveal important information about the overall structure and dynamics of the universe. As researchers observe these galaxy clusters, they measure their velocities and the directions in which they are moving. The intriguing aspect of dark flow is that it suggests there is some unseen gravitational influence pulling these clusters in a particular direction, which is not fully accounted for by the visible matter and known dark matter in our local universe. This could imply the presence of large-scale structures in the universe that we have yet to fully understand, possibly extending beyond the observable universe itself. By analyzing clusters that are located at various distances from us, scientists can trace the flow of movement and gather evidence about this mysterious force or structure that seems to be influencing the motion of these massive groups. Furthermore, these galaxy clusters serve as natural laboratories for studying the effects of gravity on a cosmic scale, as their immense mass has a significant impact on the surrounding space-time, bending light and influencing the paths of nearby galaxies. This gravitational lensing effect allows astronomers to map the distribution of dark matter within and around these clusters, providing further insights into the nature of dark flow. Additionally, as we gather more data from various observatories, including the Hubble Space Telescope and ground-based observatories, we can refine our understanding of how these clusters interact with the cosmic web, which is a vast network of galaxies and dark matter filaments that make up the large-scale structure of the universe. Researchers are continuously looking for patterns in the velocities and directions of these clusters, hoping to uncover more about the underlying mechanics of dark flow. They use advanced simulations and models to predict how these movements should behave according to established theories, and then compare these predictions with real observational data. Any discrepancies between the two could point towards new physics, perhaps revealing aspects of the universe that remain hidden from our current understanding. The study of galaxy clusters in relation to dark flow not only enhances how the distribution of galaxies has been a crucial aspect in the investigation of dark flow, a phenomenon suggesting that large-scale structures in the universe may be moving in a specific direction, influenced by gravitational forces beyond what we can currently observe. Researchers have utilized extensive surveys of galaxy distributions, mapping the positions and velocities of galaxies across vast regions of the cosmos. The process begins with collecting data from various astronomical surveys, which often employ advanced telescopes and imaging techniques. such as the Sloan Digital Sky Survey, which has provided a wealth of information about the spatial arrangement of galaxies. Clustering patterns. By analyzing this data, astronomers can create a three-dimensional map of the universe, allowing them to identify peculiar motions of galaxies that deviate from the expected Hubble flow, which describes how galaxies move away from each other due to the expansion of the universe. To specifically investigate dark flow, scientists look for signs of coherent motion among clusters of galaxies. This involves measuring the velocities of galaxies relative to the cosmic microwave background radiation, which serves as a reference point for the overall motion of the universe. By studying how galaxy clusters move, researchers can identify patterns that might indicate they are being pulled toward a larger mass, possibly a supercluster or some other unseen structure that exerts a gravitational influence. The analysis typically employs statistical methods, such as Monte Carlo simulations, to understand the significance of the observed motions compared to random distributions expected from cosmic expansion. One key study, led by a team of astrophysicists, focused on the motion of galaxies in the vicinity of the cosmic microwave background, finding that galaxies in certain regions of the sky appeared to be moving in the direction of the Great Attractor, a massive gravitational anomaly located in the Centaurus constellation. This suggested that there could be an underlying structure not fully accounted for by the visible matter we can observe that is influencing the motion of galaxies. The findings have sparked significant interest and debate within the scientific community, as they hint at the existence of dark matter or even larger structures in the universe that we have yet to fully comprehend. Furthermore, analyzing the distribution of galaxies also involves studying the cosmic web, a vast structure formed by galaxies and dark matter. Researchers map the filaments and voids of this web, observing how galaxies are not uniformly distributed, but rather clustered in groups. And along these filaments, the movement along these filaments can provide insights into the gravitational influences at play, and whether they might be part of a larger dark flow when it comes to studying dark flow phenomena. Scientists rely on a variety of advanced instruments and telescopes that help unravel the mysteries of the universe, particularly those involving the motion of galaxies and large-scale structures. One of the primary tools utilized in this research is the cosmic microwave background, or COMB, which represents the afterglow of the Big Bang and provides a snapshot of the early universe. Instruments like NASA's Wilkinson Microwave Anisotropy Probe, or WARMAP, have been pivotal in mapping the COMB, revealing patterns and fluctuations that scientists interpret to understand cosmic structures, including dark flow. Another critical observatory is the Planck spacecraft, which has taken over where WARMAP left off, offering even finer details of the COMB and enhancing our understanding of dark energy and dark matter interactions. Bye. Analyzing the subtle temperature variations in the COMB, researchers can infer the presence of large-scale flows in the universe, including dark flow, which appears to be a movement of galaxy clusters towards a particular direction, possibly hinting at gravitational influences from structures beyond the observable universe. In addition to satellite, Based observatories, ground-based telescopes play a vital role in studying dark flow phenomena. The Sloan Digital Sky Survey, or SDS, is one such project, which has mapped millions of galaxies, allowing astronomers to track their movements and study the large-scale structures of the universe. The data collected helps identify unusual clustering of galaxies that could be indicative of dark flow. Adaptive optics systems, which are used in ground-based telescopes like the Keck Observatory in Hawaii, enable astronomers to correct for atmospheric distortion, enhancing the clarity of images and improving measurements of galaxy positions and velocities. These advancements allow scientists to examine the dynamics of galaxy clusters more effectively, providing deeper insights into the nature of dark flow. Moreover, radio telescopes such as the Atacama Large Millimeter Array or ALMA play a significant role in studying the gas and dust within galaxies, which can be influenced by dark flow phenomena. By observing how these materials move and interact, researchers can gain clues about the gravitational forces at play, which may be connected. In the realm of theoretical work, simulations and models are also crucial. Researchers use supercomputers to simulate the behavior of galaxies and cosmic structures under various conditions, testing hypotheses about dark flow and its implications for cosmic evolution. These simulations help bridge the gap between observational data and theoretical understanding, contributing to a more comprehensive picture of theoretical frameworks. In space exploration and astrophysics serve as essential tools for understanding the vast complexities of the universe, guiding scientists in making sense of observations, experiments, and predictions. One of the most prominent frameworks is Einstein's general theory of relativity, which transformed our understanding of gravity, suggesting that massive objects like planets and stars warp the fabric of space-time, leading to phenomena such as the bending of light around massive celestial bodies, a concept known as gravitational lensing. This theory has been confirmed through numerous observations, like the famous Eddington experiment during a solar eclipse in 1919, which provided evidence that light from distant stars is indeed bent by the sun's gravitational field, supporting Einstein's prediction. Another significant theoretical framework is the Standard Model of particle physics, which describes the fundamental particles that make up the universe and how they interact through fundamental forces. This model includes particles like quarks, leptons, and bosons, with the Higgs boson being a crucial discovery made at CERN in 2012, confirming how particles acquire mass. The Standard Model, while incredibly successful, still leaves questions unanswered, such as the nature of dark matter and dark energy, which together make up about 95% of the universe, yet remain elusive to direct detection. In cosmology, the Big Bang Theory provides a theoretical framework for understanding the origin of the universe, suggesting it began as a singularity around 13.8 billion years ago and has been expanding ever since. This framework is supported by several key pieces of evidence, including the cosmic microwave background radiation, which is the afterglow of the Big Bang, and the observed redshift of distant galaxies. indicating that the universe is still expanding. However, researchers are continually testing and refining this model, exploring concepts like cosmic inflation, which suggests that the universe underwent rapid expansion in its early moments, smoothing out imperfections and leading to the uniform cosmos we observe today. Astrobiology also employs theoretical frameworks to explore the possibility of life beyond Earth. The Drake equation is a famous attempt to estimate the number of active, communicative extraterrestrial civilizations in the Milky Way galaxy, taking into account factors like star formation rates, the fraction of stars with planets, and the probability of life developing on those planets. While the equation is more of a thought experiment than a precise calculation, it highlights the variables involved in the search for extraterrestrial life, guiding researchers on where to look and what to study. Moreover, string theory presents a more speculative dark flow, is a term that has intrigued astronomers and cosmologists, as it refers to the mysterious movement of galaxy clusters that seem to be moving in a specific direction, away from our local group of galaxies, at a speed that cannot be accounted for by the known structures of the universe, or by the expansion driven by dark energy. This phenomenon suggests that there may be influences beyond the observable universe, and several theories have emerged to explain dark flow, each attempting to unravel this cosmic enigma. One prominent theory posits that dark flow could be the result of gravitational effects from structures that lie outside the observable universe, suggesting that there may be vast, massive objects, or even superclusters, that we cannot see, exerting a pull on the galaxies within our realm. This idea challenges the conventional understanding of the cosmos, as it implies that there is more to the universe than what we can observe, and it raises questions about the limits of our current observational technologies. Another theory suggests that dark flow may be linked to the residual effects of the Big Bang, where the universe's early moments were filled with high-energy particles and gravitational waves that could have left imprints on the large-scale structure of the cosmos. These early cosmic events might have created irregularities in the distribution of matter that could influence the motion of galaxies. Additionally, some researchers speculate that dark flow might be a manifestation of interactions with neighboring universes, or even the presence of a multiverse, where our universe is just one of many, each with its own physical laws and structures. This hypothesis is quite radical and remains a topic of intense debate among physicists, as it challenges the very foundations of our understanding of reality. Yet it opens up fascinating avenues for exploration. Moreover, there is the possibility that dark flow could be related to the influence of dark energy, which is thought to be responsible for the accelerated expansion of the universe. If dark energy has varying effects across different regions of the cosmos, it might create localized gravitational anomalies that could explain the observed movements of galaxy clusters. This theory intertwines with the concept of cosmic inflation, suggesting that the expansion of the universe might not be uniform, leading to regions of different densities and gravitational pulls that could drive the peculiar motions we observe. In essence, dark flow remains one of the universe's great puzzles, prompting scientists to look deeper into the nature of space and time, while challenging our comprehension of the cosmos and pushing the boundaries of theoretical physics. As research continues, the quest to understand cosmic inflation, a theory proposed in the early 1980s, suggests that the universe underwent an incredibly rapid expansion in its first moments, expanding faster than the speed of light, which smoothed out any irregularities, and we observe in the cosmic microwave background radiation today. This expansion not only explains the large-scale structure of the universe, but it also plays a crucial role in understanding various phenomena, including dark flow, a term that refers to the peculiar motion of galaxy clusters that appear to be moving in a specific direction, defying the expected anisotropy of the universe. As researchers have studied the cosmic microwave background, they've noticed that certain galaxy clusters seem to be moving towards a specific region of the sky, which raises intriguing questions about the underlying reasons for this motion. One hypothesis is that this dark flow could be a remnant of the initial conditions set by cosmic inflation, where the rapid expansion not only stretched space, but also influenced the distribution of matter and energy throughout the universe. The idea is that after cosmic inflation, as the universe began to cool and matter started to clump together, the gravitational influences of nearby structures, perhaps those formed during the inflationary period, could create a sort of pull on galaxy clusters, leading to their observation. This could suggest that certain regions of space are still feeling the effects of those early inflationary forces, which is a fascinating concept, as it implies that the early universe's dynamics are still influencing the behavior of galaxies billions of years later. Moreover, the concept of dark flow raises questions about the uniformity of the universe. If cosmic inflation was supposed to create a homogeneous universe, then why do we see these large-scale motions? This tension between the predictions of inflation and the observations of dark flow has led scientists to explore new models of cosmology. Considering factors like the influence of dark energy, the existence of large structures beyond the observable universe, and even the possibility of interactions with other universes, which could all play a role in these phenomena. In essence, the relationship between cosmic inflation and dark flow is part of a larger tapestry of cosmic evolution, where the echoes of the universe's infancy may still resonate through its vastness. Understanding how these two concepts interconnect not only helps in piecing together the history of our universe, but also deepens our knowledge of fundamental physics, the nature of dark energy, and the ultimate fate of everything we see around us. Dark flow, a term that has intrigued astronomers and physicists alike, refers to a peculiar phenomenon observed in the motion of galaxy clusters, specifically their movement towards a certain region in the sky, which is not easily explained by the known gravitational influence. This phenomenon was first reported in 2008, when researchers noticed that some galaxy clusters were moving in a consistent direction, seemingly towards a specific point in the cosmic microwave background radiation, a remnant from the Big Bang. The intriguing question arises: can this dark flow be explained by existing theories of gravity, or does it require new physics altogether? To delve into this, it's essential to consider how gravity, as described by Newton and later refined by Einstein's general relativity, governs the movements of celestial bodies. According to these established theories, the motion of galaxies and galaxy clusters should primarily be influenced by the gravitational pull of nearby mass, including dark matter. However, the observed dark flow suggests that there might be additional forces or influences at play, since the clusters are moving in a direction that does not correlate with the known mass distribution in our universe, which raises questions about our understanding of gravitational dynamics on a cosmic scale. Some scientists have proposed that dark flow could be a result of large-scale structures in the universe, such as the gravitational pull from superclusters of galaxies, or even from regions beyond the observable universe. This idea suggests that while our current theories of gravity may explain many phenomena effectively, they might not fully account for the complexities of cosmic flows and the large-scale structure of the universe. Others speculate that dark flow could indicate the presence of previously unknown forms of matter or energy, or even hint at interactions with other universes, as some theories in cosmology suggest. On the other hand, certain researchers argue that the measurements and interpretations of dark flow could be influenced by systematic errors or biases in the data collection methods, which raises the possibility that dark flow might not represent a new physical phenomenon, but rather an artifact of the observational techniques employed. If this is the case, it would mean that existing theories of gravity remain robust, adequately explaining the observed motions when all factors are properly accounted for. In summary, while existing theories of gravity provide a solid framework for understanding many cosmic phenomena, the mysterious nature of dark flow challenges our current models and invites further investigation. It may indeed require new physics, or at least a refinement of existing theories, to fully comprehend the forces at play in the vast expanse of the universe. The large-scale structure of the universe, which includes galaxies, galaxy clusters, and the vast voids between them, plays a crucial role in our understanding of dark flow, a mysterious phenomenon that suggests some regions of the universe are moving in a specific direction by gravitational forces beyond our observable horizon. This large-scale structure acts as the framework through which we can analyze the distribution of mass in the universe, which is essential when trying to understand dark flow, as it can affect the motion of galaxies and galaxy clusters. Observations indicate that while galaxies are generally distributed randomly on larger scales, they tend to form a web-like structure, often referred to as the cosmic web, where filaments of galaxies are interconnected and vast empty spaces, or voids, exist. When astronomers study this cosmic web, they can trace how matter is distributed and how it influences gravitational pulls on nearby structures, which may help explain why certain clusters of galaxies appear to be moving in the same direction, an observation that raises question about the existence of mass that we cannot see, often referred to as dark matter. Dark flow, observed through the motion of galaxies, appears to suggest that these galaxies are being pulled towards areas beyond the observable universe, leading scientists to hypothesize that there may be large structures or even entire superclusters that we have yet to exerting this gravitational influence. Research has shown that this flow is not uniform, and the peculiar motions of galaxies hint toward an underlying structure, which could include vast regions of dark energy or matter that comprise the fabric of the itself. By examining the large-scale structure, scientists can model how these unseen forces may interact with visible matter, helping to refine theories about the cosmos. Furthermore, understanding the large-scale structure allows researchers to utilize statistical methods to analyze the motion of galaxies, which contributes to a deeper understanding of dark flow, as well as the expansion of the universe. Through advanced simulations and observations, like those from the Sloan Digital Sky Survey and the Planck satellite, scientists map out the large-scale structure of the universe, revealing how galaxies cluster and how their movements are influenced by gravitation interactions. These insights can provide important clues about the nature of dark flow, particularly how it may correlate with the distribution of mass in the universe, which is essential for understanding the overall dynamics of the universe. This interplay between the large-scale structure and dark flow emphasizes the importance of continued research and observation, as every new discovery could potentially simulations of the universe play a crucial role in helping scientists study dark flow, which refer to galaxy clusters moving in a direction that seems to defy the gravitational pull of visible matter. By creating sophisticated models of cosmic evolution, researchers can replicate the large-scale structure of the universe, allowing them to analyze the distribution of galaxies and the influence of dark matter. These simulations typically incorporate the known laws of physics, including gravity, to predict how matter behaves over time. As scientists run these simulations, they can observe how galaxy clusters interact with one another and how their velocities can be affected by unseen forces, which may be linked to dark energy or the gravitational effects of massive yet invisible structures beyond the observable universe. This is particularly important, as dark flow suggests that there may be regions of matter that we cannot see, influencing the motion of galaxies in ways we are just beginning to understand. Moreover, these simulations allow astronomers to test various hypotheses about the nature of dark flow, such as whether it could be a result of gravitational attraction from structures beyond the observable universe, or if it points to more exotic possibilities, like the existence of other universes or dimensions. By altering different parameters in the simulations, researchers can pinpoint how changes in dark matter density or the expansion rate of the universe might affect the observed motion of galaxy clusters, thereby gaining insights into the underlying physics of the cosmos. These computer-generated models have also led to predictions that can be tested with real observational data collected from telescopes and other instruments. For instance, by comparing the results of simulations with the actual trajectories of galaxy clusters, scientists can validate or refute theories regarding dark flow. This back and forth between simulation and observation enhances our understanding of the universe's structure and the forces at play. Furthermore, the simulations provide a way to visualize complex interactions in the universe, making it easier for scientists to communicate their findings and theories to the public, as well as to educate the next generation of astronomers and physicists. They can demonstrate how even a small amount of dark matter can influence the motion of massive structures, allowing for a deeper appreciation of the mysterious components that make up our universe. In essence, simulations serve as a vital tool in the ongoing quest to understand dark flow, offering a framework through which we can explore the unseen aspects of the cosmos, and providing a platform for testing ideas that challenge our current understanding of physics. As our technology and computational power continue to advance, cosmology, the study of the universe's origins, evolution, and ultimate fate, has profound implications for our understanding of everything from the smallest particles to the largest galaxies. One of the most significant implications comes from the observation that the universe is expanding, a discovery made in the early 20th century by astronomer Edwin Hubble. This expansion suggests that the universe was once concentrated in a very small, hot and dense state, often referred to as the Big Bang, which occurred around 13.8 billion years ago. This idea reshaped our understanding of time and space, pushing the boundaries of how we think about the cosmos. Another important aspect of modern cosmology is the role of dark matter and dark energy. Observations indicate that ordinary matter, which makes up stars, planets, and galaxies, accounts for only about 5 of the total mass, energy content of the universe. Dark matter, which does not emit, absorb, or reflect light, makes up about 27, and its presence is inferred from gravitational effects on visible matter, like the rotation of galaxies. Dark energy, on the other hand, is believed to make up roughly 68 of the universe. This raises deep philosophical questions about the nature of reality, as we cannot see or directly measure these components, yet they dominate the universe. Furthermore, the study of cosmic microwave background radiation, which is the afterglow of the Big Bang, provides a snapshot of the early universe, revealing information about its temperature fluctuations and density variations. These insights help cosmologists understand how the large-scale structure of the universe formed, leading to the galaxies and clusters we observe today. The uniformity and slight anisotropies in this radiation allow scientists to test different theories of the universe's evolution, such as inflation, which proposes a rapid expansion in the universe's first moments. The implications of cosmology extend beyond the boundaries of academic inquiry. They touch on existential questions about the nature of life and our place in the universe. The potential discovery of exoplanets in habitable zones, for instance, raises questions about whether life exists elsewhere in the cosmos. The Drake equation, formulated to estimate the number of active, communicative extraterrestrial civilizations in the Milky Way galaxy, illustrates the interplay between cosmology and astrobiology, emphasizing that our understanding of the universe could lead to profound implications. Future. Moreover, theories regarding the fate of the universe, dark flow, a term that has emerged from observations of galaxy clusters, refers to a peculiar motion of galaxies that seems to be moving in a specific direction, beyond what we would expect from the cosmic microwave background rate, the overall expansion of the universe. This intriguing phenomenon was first noted in a study led by astronomers from the University of California, Los Angeles, who observed that certain galaxy clusters, particularly those located in the southern hemisphere, exhibited a motion towards a region in the sky known as the cold spot. This cold spot, a large area of unusually low temperature in the cosmic microwave background, raises questions about the influence of large-scale structures, or possibly even the effects of forces that are not yet fully understood. Dark flow challenges our current models of cosmological expansion, which largely rely on the assumption that the universe's expansion is uniform and isotropic, meaning it looks the same in all directions. If dark flow is indeed a real phenomenon, it could imply that the universe is not only expanding, but that there are large-scale gravitational influences pulling galaxies and clusters in particular directions, suggesting that there may be structures beyond our observable significant gravitational effects. This notion invites us to reconsider the nature of dark energy, the mysterious force that is driving the accelerated expansion of the universe. If dark flow indicates that there are gravitational pulls at play, it might suggest that dark energy is not as straightforward as previously thought, and that our understanding of the forces governing the cosmos could be incomplete. Furthermore, the implications of dark flow extend to our comprehension of the cosmic web, the large-scale structure of the universe, where galaxies are interconnected through filaments and voids. Understanding how dark flow interacts with these structures could provide critical insights into how galaxies form and evolve over time. In essence, dark flow could alter our perception of the universe's topology, shedding light on regions that are currently beyond our observational reach. If there are massive structures influencing galaxy motion beyond the observable universe, this could mean that our current models of cosmology, which are primarily based on observations within our limited cosmic horizon, require significant refinement. As we delve deeper into the mysteries of dark flow, Astronomers and physicists are encouraged to re-evaluate the fundamental principles of how we perceive the universe's expansion, potentially leading to groundbreaking discoveries that could reshape our understanding of astrophysics, cosmology, and the very nature of reality itself. The ongoing research into dark flow not only highlights the complexities of the cosmos, but also underscores the importance dark flow is a fascinating phenomenon in cosmology, referring to the observed motion of galaxy clusters, which appears to be moving in a specific direction. The influence of local gravitational forces. This motion raises intriguing questions about the structure and evolution of the universe. Regions of large-scale anisotropy, on the other hand, refer to areas in the universe where physical properties such as density and temperature are not uniform, but rather exhibit directional dependence. This means that the universe is not perfectly isotropic, or the same in all directions, which is a key assumption of the cosmological principle. The potential connections between dark flow and large-scale anisotropy are thought-provoking, as they suggest that the universe may have underlying structures that influence the motion of galaxies on a grand scale. One hypothesis is that dark flow may be related to the gravitational effects of massive structures, such as superclusters or vast voids that create a pull on the surrounding matter. These massive structures may create a kind of cosmic landscape where the distribution of galaxies is not uniform, leading to regions of anisotropy. Research has indicated that the regions exhibiting dark flow might be correlated with the locations of these large-scale anisotropic structures. For instance, when scientists analyze the cosmic microwave background radiation, they observe temperature fluctuations that indicate variations in density across different regions of space. These fluctuations could suggest that dark flow is not just a random motion, but rather a response to the gravitational effects of these anisotropic regions, which can guide the motion of galaxy clusters toward them. Moreover, the potential connection between dark flow and anisotropy may also provide insights into the early universe, particularly during the inflationary period, when rapid expansion occurred. If the universe underwent periods of anisotropic expansion, it might have left imprints that we observe today as dark flow. This means that the current motion of galaxy clusters could be a remnant of these early conditions, leading to a deeper understanding of how the universe evolved from a hot, dense state to the large-scale structure we see today. Some researchers have suggested that exploring the connection between dark flow and anisotropy could help us understand dark energy, a mysterious component of the universe that is believed to drive its accelerated expansion. If dark flow is influenced by anisotropic regions, it might indicate that dark energy itself has a non-uniform distribution, challenging our current models of the cosmos. This exploration could lead to new theories about the fundamental forces shaping the universe, and how the cosmologists employ various methods to differentiate between dark flow and other cosmic flows. like the peculiar motion of galaxies, which can be quite complex, yet fascinating. To begin with, dark flow refers to a peculiar motion of galaxy clusters that seems to be moving in a specific direction, beyond what we would expect, based solely on the influence of observable matter and radiation. This concept emerged from observations based on the cosmic microwave background radiation, which is the afterglow of the Big Bang, revealing a slight anisotropy or irregularity in the motion of galaxy clusters, suggesting that they are moving towards a region in the universe that is not accounted for by known gravitational influences. On the other hand, the peculiar motion of galaxies is their individual movement relative to the average motion of galaxies in the universe. This peculiar motion is typically caused by gravitational interactions, such as the pull from nearby galaxies or clusters, as well as the overall expansion of the universe described by Hubble's law. To distinguish between these two phenomena, cosmologists analyze redshift data, which measures how light from distant galaxies shifts toward the red end of the spectrum as they move away from us. By studying the redshifts, numerous galaxies and galaxy clusters, scientists can calculate their velocities and directions, allowing them to map out the peculiar motions. In cases where a group of galaxies shows a consistent movement that deviates from the expected cosmic flow, it may indicate the influence of dark flow. Additionally, researchers utilize simulations and models of the large-scale structure of the universe to predict how galaxy clusters should behave under the known laws of physics, including gravitational interactions and dark energy effects. If observations consistently show a group of galaxy clusters moving in a direction that cannot be explained by these models, it provides evidence of dark flow. Furthermore, cosmologists also compare the statistical distribution of galaxy clusters with the expected distribution from the standard cosmological model, known as the lambda cold dark matter model, which incorporates dark matter, dark energy, and the expansion of the universe. By looking at the large-scale structure, they can identify anomalies that suggest dark flow, rather than just local gravitational influences. Different data sets, such as those from galaxy surveys or cosmic microwave background measurements, help scientists cross-check their findings and strengthen their conclusions. Through these various analytical methods, cosmologists can piece together a clearer picture of the universe's dynamics, revealing the unique characteristics of dark flow in contrast to the more common peculiar motions of galaxies. The ongoing investigation into these cosmic flows, not only dark flow is a term used to describe a mysterious phenomenon observed in the motion of galaxy clusters, and it holds significant implications for our understanding of the cosmic web, which is the large-scale structure of the universe. The cosmic web is made up of filaments of galaxies and dark matter, interconnected in a vast network with enormous voids in between. Observations have shown that certain galaxy clusters are moving towards a specific region of the sky, seemingly influenced by gravitational forces from areas beyond the observable universe. This directed motion is what scientists refer to as dark flow, and its significance lies in the insights it provides into the nature of the universe and the distribution of matter on the largest scales. The discovery of dark flow challenges our understanding of the cosmic microwave background radiation, which is the afterglow of the Big Bang that pervades the universe. This radiation is remarkably uniform, but if dark flow is occurring, it suggests that there may be massive structures, or even entire regions of matter, beyond the observable limits of our universe. These regions could exert gravitational effects on the galaxy clusters we can observe, pulling them towards themselves, thus indicating that our understanding of the universe might be incomplete, or that there could be larger scales of structure that we are currently unaware of. Moreover, dark flow raises questions about the anisotropy of the universe, which is the idea that the universe looks the same in all directions. If galaxy clusters are moving in a preferred direction, as the dark flow suggests, it implies that there might be a cosmic bias in the distribution of mass, which could affect the formation of galaxies and the evolution of the universe as a whole. This could lead to new theories about the formation of the cosmic web and how galaxies form and evolve within it, as well as how they are influenced by the surrounding dark matter and energy. Additionally, dark flow has ties to the concept of dark energy, which is the mysterious force driving them. Accelerated expansion of the universe. If dark flow is indeed associated with structures outside our observable universe, it might provide clues about the nature of dark energy and its role in cosmic expansion. Understanding how dark flow interacts with the cosmic web could lead to breakthroughs in our comprehension of fundamental physics, including gravity, and may even inform us about the fate of the universe. In summary, the significance of dark flow in relation to the cosmic web is profound, as it not only challenges existing theories about the universe's structure and distribution of matter, but also opens up new avenues for research into the existence of dark flow, observed in the motion of galaxy clusters, could significantly challenge the current cosmological model, particularly our understanding of the large-scale structure of the universe. Dark flow refers to the motion of galaxy clusters that appear to be moving in a specific direction, towards a point in the sky, beyond what would be expected from the gravitational influence of visible matter alone, or from the known cosmic microwave background radiation. This peculiar movement raises questions about the anisotropy of the universe, which is a core assumption of the cosmological principle, stating that the universe is homogeneous and isotropic on large scales. If dark flow is confirmed, it suggests that there are structures or influences beyond our observable universe, possibly indicating the presence of a large supercluster or even a region of space that we cannot and the expansion. In essence, dark flow could imply that our universe is not as uniform as we once thought, suggesting that there could be a vast unexplored territory influencing galaxy motions, perhaps indicating interactions with other universes. This could challenge the current models of cosmic evolution, requiring physicists and astronomers to reconsider the forces and dynamics that govern the universe. Moreover, if dark flow were linked to new physics, it could provide insights into phenomena like dark energy, which is already a significant challenge in understanding cosmic acceleration. The implications of dark flow might extend to the nature of dark matter itself, further unraveling the mysteries surrounding the universe's composition. Additionally, the existence of dark flow could lead to new avenues of research in cosmology, prompting investigations into the structure of the universe on the largest scales. It might encourage scientists to develop new theoretical frameworks that incorporate this phenomenon, potentially leading to a unified theory that reconciles dark matter, dark energy, and the observed cosmic microwave background. As researchers delve deeper into the cosmic web, examining the relationships between galaxies, clusters, and dark flow, they may uncover fundamental truths about the universe's past, present, and future. This scenario emphasizes the necessity for continued observation and data collection from telescopes and observatories, as well as the importance of collaboration across disciplines, bringing together astrophysicists, cosmologists, and theoretical physicists to piece together the puzzle, flow, and its implications for our understanding of the cosmos. The unfolding story of dark flow invites us to reconsider the boundaries of our knowledge, challenging us. Investigative techniques play a crucial role in the exploration of space and the universe, helping scientists and researchers uncover the mysteries of celestial bodies, cosmic phenomena, the very fabric of reality itself. One of the most effective techniques used in space exploration is remote sensing, which involves collecting data from a distance, often through satellites or telescopes. For instance, telescopes like the Hubble Space Telescope utilize remote sensing to capture stunning images of distant galaxies and nebulae, revealing details that are otherwise invisible to the naked eye. This technique allows astronomers to study the composition, temperature, and motion of celestial objects, providing insights into their formation and evolution. Another important technique is spectroscopy, a method that analyzes the light emitted or absorbed by substances in space. By examining the spectrum of light from stars, planets, and other celestial objects, scientists can determine their chemical composition, temperature, density, and even the presence of organic molecules. This technique has been instrumental in the search for exoplanets, as it allows researchers to identify the atmospheric conditions that could support life. For example, the discovery of water vapor in the atmosphere of exoplanets has raised exciting possibilities about the potential for life beyond Earth. In addition to remote sensing and spectroscopy, computer modeling is a vital investigative technique in understanding cosmic phenomena. Scientists use complex algorithms and simulations to model the behavior of celestial bodies, such as the formation of galaxies or the dynamics of black holes. These models can predict how these objects evolve over time, helping researchers test their theories against observational data. For instance, simulations of galaxy formation have shown how dark matter influences the structure of galaxies, providing a deeper understanding of the universe's evolution. Moreover, direct observation is another key technique in space investigation. Space missions, such as those conducted by NASA and other space agencies, send spacecraft to gather data from planets, moons, and asteroids up close. The Perseverance rover, currently exploring Mars, utilizes various instruments to analyze the Martian surface, search for signs of ancient life, and collect samples for future return to Earth. This hands-on approach allows scientists to gain first-hand knowledge about the Martian environment and its geological history. Furthermore, gravitational wave detection has emerged as a groundbreaking technique in astrophysics. When massive objects like black holes collide, they create ripples in the fabric of space-time, known as gravitational waves. Detectors like LIGO and Virgo have successfully captured these waves, providing new ways to observe cosmic events that are otherwise invisible. To understand dark flow in the universe, scientists employ a variety of observational techniques, each aimed at unraveling the mysteries of this enigmatic phenomenon. Dark flow, which refers to the peculiar motion of galaxy clusters, seems to suggest that there are large-scale structures beyond our observable universe influencing the movement of these clusters. One of the primary techniques used to quantify dark flow is the measurement of the cosmic microwave background radiation, or COM, which is the afterglow of the Big Bang. By analyzing the temperature fluctuations in the COM, researchers can detect patterns that indicate the motion of galaxy clusters relative to this ancient radiation, revealing how they are being pulled by unseen forces. Another critical method involves the use of redshift surveys, where astronomers measure the redshift of light coming from distant galaxies. As galaxies move away from us, their light shifts to longer wavelengths, and this redshift can be quantified. By observing the redshift of numerous galaxies, scientists can map their velocities and directions, allowing them to identify any coherent motion that deviates from the expected expansion of the universe. This technique has revealed that certain galaxy clusters are moving in a direction that suggests they are influenced by gravitational forces from regions not fully accounted for by our current understanding of cosmic structures. Additionally, the use of gravitational lensing plays a significant role in studying dark flow. Gravitational lensing occurs when the gravity of a massive object, like a galaxy cluster, bends the light from objects behind it. By analyzing the distortions in the images of distant galaxies caused by this lensing effect, researchers can infer the mass distribution of the lensing object and, consequently, the dynamics of the surrounding universe. This helps scientists understand how dark flow affects the motion of galaxy clusters in relation to the larger cosmic web. Moreover, Advanced simulations and computational models are utilized to predict the expected behavior of galaxy clusters based on known cosmic structure. By comparing these simulations with actual observations, researchers can identify anomalies in cluster motion, providing evidence for dark flow. Observatories equipped with powerful telescopes, such as the Hubble Space Telescope and the upcoming James Webb Space Telescope, enable astronomers to gather high-resolution data on distant galaxies, enhancing our understanding of their dynamics and the potential influences of dark flow. In recent years, the study of peculiar velocities has also gained attention. By examining the velocities of galaxy clusters and how they differ from the overall expansion of the universe, researchers can gain insights into the gravitational interactions at play. This can help quantify the extent redshift surveys play a significant role in our understanding of dark flow, a mysterious phenomenon that suggests the existence of large-scale motions in the universe, which cannot be accounted for by the cosmic microwave background or by the known distribution of matter. To grasp how redshift surveys contribute to this understanding, it's essential to first understand what redshift is. Essentially, redshift occurs when light from an object in space is stretched, making it appear redder as it moves away from us, This stretching happens due to the expansion of the universe as described by Hubble's law. By measuring the redshift of light from distant galaxies, astronomers can determine how fast those galaxies are moving away from us. Now, when we conduct redshift surveys, we collect data from a vast number of galaxies, mapping their positions. This extensive dataset allows scientists to analyze the large-scale structure of the universe, revealing how galaxies are distributed and how they move within cosmic voids and filaments. Dark flow comes into play when we begin to notice unexpected patterns in this distribution. Some studies suggest that certain galaxy clusters are moving in a direction that does not align with the expected isotropic expansion of the universe. This anomaly hints at the influence of gravitational forces from massive structures located beyond the observable universe. The findings from redshift surveys help astronomers to identify these peculiar motions, as they can compare the velocities of galaxies against the cosmic microwave background radiation, which provides a reference point for the overall expansion of the universe. If galaxies are moving in a direction that deviates from what we anticipate, this could indicate the presence of unseen mass or structures, perhaps even entire regions of space that we cannot directly observe, but which exert gravitational pull on visible matter. As researchers gather more data from various redshift surveys, they can refine their models of cosmic flow and better understand the underlying forces at work. Moreover, redshift surveys have also revealed large voids and superclusters, which serve as gravitational lenses, affecting the movements of galaxies within their vicinity. These observations lead to hypotheses regarding the influence of dark matter and dark energy, both of which are integral to the current understanding of cosmic dynamics. The interaction between these components and the observable matter can create the conditions necessary for dark flow, as the gravitational influences may pull galaxies towards unseen structures. As scientists continue to analyze the results from Redshift surveys, they develop more sophisticated simulations and models that incorporate these observed motions. By doing so, in the study of dark flow, which refers to the peculiar motion of galaxy clusters that seems to deviate from the general expansion of the universe, researchers employ several statistical methods to analyze the complex data involved. One of the primary techniques used is the analysis of variance, or ANOVA, which helps scientists determine whether there are significant differences in the velocities of galaxy clusters across different regions of the sky. By comparing these velocities, researchers can identify patterns that might suggest the presence of gravitational influences from unseen mass, possibly related to dark matter or other cosmic structures. Another important method is the use of regression analysis, which allows scientists to model the relationship between the observed velocities of galaxy clusters and various factors, such as distance or the density of matter in the surrounding regions. This can help in understanding how these clusters are moving and how they might be influenced by the large-scale structure of the universe. In addition to regression, clustering algorithms which group together similar data points based on their velocities are often applied to identify potential trends and anomalies in the data. Cosmological simulations, which create virtual universes based on physical laws and parameters, also play a crucial role in analyzing dark flow. By comparing the observed motion of galaxy clusters with the predictions from these simulations, researchers can gauge whether the observed data aligns with theoretical models, or if there are discrepancies that might indicate new physics at play. Bayesian methods are frequently used as well, providing a framework for updating the probability of a hypothesis as more data becomes available, thus allowing scientists to refine their understanding of dark flow over time. Additionally, the use of Monte Carlo simulations enables researchers to explore a wide range of possible scenarios and uncertainties in their data, which is essential given the sparse and often noisy nature of astronomical observations. These computational techniques help to create a statistical foundation upon which conclusions about dark flow can be made, giving scientists a better grasp of the underlying cosmic phenomena. Ultimately, the combination of these statistical methods, along with robust data collection from various astronomical surveys, creates a comprehensive approach to deciphering the mysteries of dark flow and its implications for our understanding of the universe. Machine learning has become a powerful tool in the quest to understand dark flow, a mysterious phenomenon that refers to the observation of large-scale motion of galaxy clusters that seems to be directed towards a specific region in the universe, raising intriguing questions about the influence of unseen mass. Researchers have employed machine learning algorithms to analyze vast datasets, which include cosmic microwave background radiation, galaxy surveys, and simulations of the universe's large-scale structure. These algorithms can identify patterns and correlations that might be difficult for human analysts to discern, especially given the complexity of the data involved. For example, supervised learning techniques have been used to classify galaxy clusters based on their motion, helping scientists to differentiate between the effects of gravitational interactions and the potential influence of dark flow. Furthermore, unsupervised learning methods, such as clustering algorithms, have been utilized to group galaxies based on their velocities and spatial distributions, revealing underlying structures in the universe that may be related to dark flow. This approach can highlight anomalies or unexpected behaviors in galaxy clusters that could be tied to the gravitational pull from massive structures beyond the observable universe, which is a key aspect of the dark flow hypothesis. Also, by employing neural networks, researchers can create models that predict the behavior of galaxy clusters under various cosmological conditions, giving insights into how dark flow interacts with the expansion of the universe and the distribution of dark matter. Additionally, machine learning has facilitated simulations that explore different cosmological models, allowing scientists to test the dark flow hypothesis against alternative explanations for the observed motion of galaxy clusters. These simulations can incorporate a range of parameters, including the influence of dark energy, the density of matter, and the geometry of the universe, providing a robust framework for understanding how dark flow fits into the larger cosmological picture. As more data becomes available from upcoming surveys, such as the Vera-C, Rubin Observatory's legacy survey of space and time, machine learning techniques will become increasingly vital in refining our understanding of dark flow and its implications for our knowledge of the universe. The ability of machine learning to process large volumes of data efficiently means it can uncover new insights that could reshape our understanding of cosmic phenomena, including dark flow. By analyzing the interactions between galaxies, the influence of gravitational forces, and the overall structure of the universe, scientists are hopeful that machine learning will not only provide clarity on dark flow, but will also contribute to our understanding of the fundamental forces that govern the cosmos. In this way, machine learning stands out as a promising frontier in the study of dark flow and other enigmatic aspects. Researchers face numerous challenges when trying to isolate dark flow from other cosmic signals, primarily due to the vast complexity and dynamic nature. Dark flow, a mysterious phenomenon suggested by some studies, indicates that galaxy clusters are moving in a specific direction, seemingly influenced by something beyond the observable universe. However, distinguishing this subtle movement from the myriad of other cosmic signals is no small feat. One major challenge is the sheer amount of noise generated by various sources, including cosmic microwave background radiation, which is the afterglow of the Big Bang. This radiation permeates the universe and can easily obscure the faint signals researchers are trying to detect. Moreover, the motion of galaxies and galaxy clusters is influenced by a variety of gravitational forces, including those from nearby galaxies, dark matter and dark energy. This means that researchers must develop sophisticated models to account for these influences, making it difficult to isolate the specific signal of dark flow. Additionally, the instruments used to detect these signals must have extremely high precision, as dark flow is theorized to be a very subtle effect, often lost within the noise of cosmic radiation and the gravitational influences of other massive structures. Another layer of complexity arises from the fact that our universe is constantly expanding, with galaxies moving away from each other due to the expansion of space itself. This expansion can create redshift effects that complicate the interpretation of data. Researchers need to disentangle this redshift from the actual motion they are trying to measure. Furthermore, different regions of the universe may exhibit varying behaviors, so isolating dark flow requires extensive surveys of the cosmos, covering large volumes of space and time. And this can be both resource-intensive and time-consuming. Data collection is also a challenge, as many of the existing observational facilities may not be equipped to capture the nuances of dark flow signals. Some telescopes may be limited in their sensitivity or resolution, which can hinder the detection of these subtle cosmic movements. As a result, researchers often have to rely on multiple observational campaigns, combining data from different telescopes and instruments in hopes of corroborating their findings through independent measurements. Finally, there is also ongoing debate within the scientific community regarding the existence and interpretation of dark flow itself. Some researchers argue that the evidence is not strong enough to conclude that it exists, while others believe that it could be a significant indicator of large-scale structures in the universe. This lack of consensus can create additional hurdles when it comes to formulating a unified approach to isolating dark flow from other cosmic signals. Ongoing research in the field of space and the universe is a fascinating endeavor, as scientists and astronomers are pushing the boundaries of our knowledge. One of the most exciting areas of research is the study of dark matter and dark energy, which together make up about 95% of the universe. Scientists are using advanced telescopes and particle detectors to gather data, hoping to unlock the mysteries of these elusive components that seem to influence the expansion of the universe, yet remain invisible to direct observation. Researchers are also delving into the cosmic microwave background radiation, which is the afterglow of the Big Bang, to glean insights about the early universe and the formation of galaxies. Additionally, the search for exoplanets, or planets outside our solar system, continues to captivate researchers. With missions like the Transiting Exoplanet Survey satellite, known as TESS, and the James Webb Space Telescope, scientists are discovering new worlds some of which lie in the habitable zone where conditions might be right for life. This research not only expands our understanding of planetary systems, but also fuels the search for extraterrestrial life, a quest that has fascinated humanity for centuries. The methods used to detect these exoplanets, such as the transit method and radial velocity technique, are becoming increasingly refined, leading to the discovery of smaller and more Earth-like planets. Another area of ongoing research is the study of black holes, particularly the supermassive black holes that reside at the centers of galaxies. The Event Horizon Telescope collaboration made headlines in 2019 when it captured the first image of a black hole located in the galaxy Mighty 7. This kind of research sheds light on the nature of these mysterious objects, their formation, and their role in galaxy evolution. Scientists are also investigating the gravitational waves produced by colliding black holes, which were first detected in 2015, providing a new way to observe the universe and test the fundamental theories of physics. Astrobiology, the study of life in the universe, is another vibrant field of research. Scientists are examining extreme environments on Earth, such as deep-sea vents and acidic lakes, to understand how life can survive in harsh conditions, which may provide clues about potential life on other planets or moons, like Europa or missions to Mars are also a key focus, with rovers like Perseverance and Curiosity exploring the Martian surface, searching for signs of past current research projects focused on unraveling dark flow, are delving into some of the most mysterious aspects of our universe. Peculiar motion of galaxy clusters, which seem to be moving in a specific direction rather than being uniformly distributed in space, was first noticed in 2008 when a team of astronomers led by Alexander Kashlinsky reported that certain clusters of galaxies were moving at great speeds, far exceeding what could be explained by the gravitational influence of nearby matter. Since then, several research teams have been working to better understand this enigmatic motion. One prominent project involves the use of advanced telescopes, like the Hubble Space Telescope and the upcoming James Webb Space Telescope, which is equipped with powerful infrared capabilities, allowing scientists to observe distant galaxies and gather data on their redshifts and velocities. Researchers are meticulously analyzing cosmic microwave background radiation, which provides crucial information on the early universe and could help illuminate the underlying causes of dark flow. Additionally, projects such as the Sloan Digital Sky Survey are collecting extensive data on the large-scale structure of the universe, mapping the distribution of galaxies and clusters, which can offer insights into the gravitational influences at play. Theoretical physicists are exploring various models, including the possibility that dark flow is caused by the gravitational pull of massive structures beyond them. Observable universe, or even interactions with other dimensions, as suggested by some theories in cosmology. Efforts are also being made to incorporate dark energy and dark matter into these models, as understanding their roles might help clarify. Collaborative international research involving institutions from around the world is crucial, as it brings together diverse expertise and resources, enhancing the capability to analyze vast amounts of data and refine theoretical frameworks. As scientists continue to gather more observational evidence and develop new simulations, the hope is to unravel the mystery of dark flow, leading to a deeper understanding of the universe's structure and evolution. The ongoing quest to understand dark flow not only addresses fundamental questions about the cosmos, but also challenges our understanding of gravity and the forces that govern the universe, making it a fascinating and vital area of research in modern astrophysics. International collaborations play a crucial role in enhancing the study of dark flow, a phenomenon that refers to the peculiar motion of galaxy clusters, which seem to be moving towards a specific region of the universe, possibly influenced by gravitational forces from unseen mass. These collaborations bring together scientists from various countries, pooling their diverse expertise, resources, and advanced technologies, which ultimately leads to a more comprehensive understanding of dark flow. For instance, researchers from different backgrounds can share their findings and methodologies, allowing for cross-validation of results and reducing the chances of bias or error that might arise from a singular perspective. Furthermore, large-scale observatories, such as the European Southern Observatory in Chile, and projects like the Sloan Digital Sky Survey in the United States, often rely on international partnerships to gather extensive data required for studying dark flow. By combining datasets from various telescopes and instruments worldwide, scientists can create a more detailed and accurate picture of the universe's structure and the forces at play. Collaboration also facilitates access to different types of technology, enabling researchers to utilize cutting-edge tools, such as advanced computational models and simulations, which are essential for analyzing the complex dynamics involved in dark flow. Moreover, these collaborative efforts often lead to joint research papers and publications, which serve to disseminate knowledge more widely across the scientific community. When scientists from different countries work together, they can leverage each other's strengths, whether it's theoretical physics, observational astronomy, or data analysis. This synergy not only enhances the quality of research, but also encourages the sharing of best practices and innovative techniques that can lead to new discoveries and insights. In addition, international collaborations can attract funding from various sources, including government grants and private sector investments, which can be crucial for conducting large-scale studies and experiments. By presenting a united front, researchers can demonstrate the global importance of understanding dark flow, thus enhancing their ability to secure necessary resources. This funding allows for the continuation of long-term projects, which are essential when studying cosmic phenomena that take time to observe and analyze. Furthermore, these collaborations often lead to the establishment of international conferences and workshops, where scientists can present their latest findings, exchange ideas, and spark new collaborations. Such gatherings foster a sense of community among researchers, encouraging a culture of open discussion and inquiry that is vital for scientific progress. As a result, new hypotheses can be generated, and existing theories can be challenged, which is fundamental to the scientific method. Lastly, international partnerships often include educational components, where younger scientists and students from various countries or recent studies have brought intriguing insights regarding dark flow, a phenomenon that suggests the existence of a mysterious gravitational influence affecting the movement of galaxy clusters. Dark flow was first proposed in 2008 when researchers observed that certain galaxy clusters, particularly those in the cosmic microwave background radiation, were moving in a direction that could not be fully explained by known cosmic structures, leading to speculation about the presence of massive, unseen structures beyond the observable universe. In the latest findings, scientists have continued to analyze data from NASA's Wilkinson Microwave Anisotropy Probe, or WAP, which has been pivotal in studying the cosmic microwave background. Newer observations have reinforced the idea that these galaxy clusters are moving with a significant velocity, about 600 kilometers per second, towards a specific point in the sky, which is near the constellations of Centaurus and Vela. This movement has raised questions about what could be causing such a flow, as standard models of cosmology do not account for this phenomenon. Some researchers speculate that this dark flow might be influenced by structures much larger than galaxy clusters, such as superclusters, or even the hypothetical Great Attractor, a gravitational anomaly in intergalactic space that appears to pull galaxies towards it. However, the exact nature and origin of dark flow remain elusive, and some scientists are cautious about drawing definitive conclusions, arguing that more data is needed to understand this peculiar behavior properly. Additionally, there have been discussions surrounding the implications of dark flow on our understanding of cosmic evolution and the overall structure of the universe. The existence of such a flow could suggest that there are vast regions of space that we have yet to explore or comprehend, potentially housing massive structures that challenge our current models of cosmology. Many in the scientific community continue to debate whether this flow is a real phenomenon or simply a product of observational bias or other local gravitational effects. Recent analyses have even suggested that dark flow may provide insights into the nature of dark matter and dark energy, as understanding these components is crucial for piecing together the universe's fabric. Researchers are now employing advanced simulations and models to further investigate how dark flow fits within the broader context of cosmic structure formation. This ongoing research highlights a critical aspect of astrophysics. As scientists strive to uncover the truth behind the universe's hidden forces and determine how they influence the cosmos on both large and small scales. As such, while dark flow continues to be a subject of fascination and inquiry, it serves as a reminder of the complexities and mysteries that lie. Dark flow research is a fascinating area of cosmology that explores the peculiar motion of galaxy clusters, which seem to move in a suggesting that there might be gravitational influences from regions beyond our observable universe. This intriguing phenomenon intersects with studies of the cosmic microwave background, or COM, which is the faint afterglow of the Big Bang, filling the universe with a uniform radiation. Detect today. The cosmic microwave background serves as a snapshot of the early universe, providing critical evidence for the Big Bang theory and helping scientists understand the large-scale structure of the cosmos. When researchers examine the COM, they look at tiny temperature fluctuations, known as anisotropies, which reveal information about the density variations in the early universe. These fluctuations are essential in understanding how matter has clumped together over billions of years to form galaxies and clusters. Now, when we consider dark flow, researchers have found that some galaxy clusters, particularly those in the local universe, exhibit a peculiar motion that seems to align with a specific direction in space, rather than moving randomly. This motion raises questions about what could be exerting this influence. Some theories suggest that dark flow could be the result of gravitational pull from massive structures located beyond the observable universe, perhaps even from regions influenced by forces we do not yet fully understand. The intersection of dark flow research and COM studies becomes particularly interesting when scientists attempt to understand the large-scale structures that may have existed in the early universe. If the gravitational influences attributed to dark flow are indeed stemming from distant regions, they could also affect the COM, particularly in the way that the anisotropies are distributed. In other words, the unique motion of galaxy clusters could provide clues about the early universe's expansion and the distribution of matter that gave rise to the cosmic microwave background we observe today. Researchers have employed sophisticated methods to analyze the COM, looking for patterns or anomalies that could be connected to dark flow. For instance, by mapping the temperature fluctuations in the COM, scientists can search for correlations between these fluctuations and the motion of galaxy clusters. If a connection exists, it could suggest that the motion of these clusters is indeed influenced by structures beyond our observable universe, thus providing deeper insights into the universe's overall architecture and its evolution. Moreover, exploring the link between dark flow and the COM can help refine our understanding of dark energy, the mysterious force thought to drive the accelerated expansion of the universe. Since dark flow suggests field of cosmology, dark flow has emerged as a fascinating and somewhat perplexing phenomenon, leading researchers to explore its implications for our understanding of the universe. Dark flow refers to the peculiar motion of galaxy clusters that seem to be moving in a specific direction, possibly indicating the influence of structures beyond the observable universe. This intriguing concept was first brought to light in the early 2000s, when astronomers analyzing the cosmic microwave background radiation detected unusual velocities in certain galaxy clusters, suggesting they were moving towards a particular region of the sky. As we look to the future, the directions for research on dark flow are manifold, focusing on both observational and theoretical aspects of this enigmatic phenomenon. One promising avenue for future research involves the use of advanced observational techniques and new telescopes that are expected to come online in the coming years. For instance, the upcoming James Webb Space Telescope, set to launch soon, aims to provide deeper insights into the structure of the universe by observing distant galaxies and cosmic phenomena in unprecedented detail. This could allow scientists to gather more accurate data on the motion of galaxy clusters, potentially revealing more about the nature of dark flow and its implications for the large-scale structure of the cosmos. Furthermore, ongoing projects like the Square Kilometre Array, which will be the world's largest radio telescope, could help map the distribution of matter in the universe and improve our understanding of any peculiar motions that might be linked to dark flow. Moreover, researchers are also looking into the theoretical frameworks that could explain dark flow. One line of inquiry examines the potential influence of dark energy or dark matter on the motion of galaxy clusters, as these mysterious components make up a significant portion of the universe's mass energy content. Some scientists propose that interactions with vast structures, such as superclusters, or even the hypothetical existence of a multiverse, could be causing the observed motions. As cosmologists continue to develop and refine models of dark energy and dark matter, they may uncover new insights that could either support or challenge the existence of dark flow. Additionally, interdisciplinary collaboration is becoming increasingly important in the study of dark flow by integrating knowledge from astrophysics, particle physics, and even computational sciences. Researchers can develop more comprehensive models that account for various factors influencing galaxy movements. This collaborative approach may lead to breakthroughs that clarify the relationship between dark flow and the overall dynamics of the universe, shedding light on how these cosmic forces interact. Another exciting direction for future research is the potential development of new simulation techniques. Advanced computer, when we look at the universe, we often find ourselves captivated by its vastness and the mysteries it holds. But what is the broader context of space exploration? And why does it matter? The exploration of space is not just about sending rockets into the cosmos. It's a journey that helps us understand our place in the universe, shaping our knowledge of fundamental science, technology advancements, and even international collaboration. For instance, the International Space Station, orbiting Earth since 1998, serves as a microcosm of international cooperation, bringing together scientists and engineers from multiple countries, each working towards common goals, studying everything from the effects of microgravity to the behavior of materials in space, all of which can lead to breakthroughs that benefit life on Earth. Furthermore, the study of asteroids and comets, which are remnants from the early solar system, provides clues about the formation of our planetary neighborhood. Missions like NASA's OSIRIS, REx, which successfully collected samples from the asteroid Bennu, are helping scientists learn about the building blocks of life and the origins of water on Earth, deepening our understanding of how life might exist elsewhere in the universe. Speaking of other worlds, the search for exoplanets has gained remarkable momentum, especially with missions like the Kepler Space Telescope and the Transiting Exoplanet Survey Satellite, or TESS, which have discovered thousands of planets outside our solar system. These discoveries are crucial as scientists analyze their atmospheres, looking for signs of habitability and even potential life, igniting our imagination about what lies beyond our home planet. Then there's the question of dark matter and dark energy, which collectively make up about 95% of the universe. While we can observe the effects of dark matter through its gravitational influence on galaxies, its true nature remains one of the biggest mysteries in astrophysics. Understanding these elusive components of the universe could revolutionize our understanding of physics and the very structure of the cosmos. Additionally, the ongoing advancements in telescope technology, such as the James Webb Space Telescope, allow us to peer deeper into space and further back in time than ever before, unveiling previously hidden phenomena and cosmic events like the birth of stars and galaxies, helping us to piece together the history of the universe and our own origins. As we venture further into space, the implications of human colonization of other planets, particularly Mars, spark both excitement and debate. Organizations like SpaceX aim to make interplanetary dark flow is a fascinating concept that relates to the mysterious phenomena of dark matter and dark energy, both of which play crucial roles in our understanding of the universe. To grasp the connection, it's important to first understand what dark flow is. Observations made around 2008, particularly by a team led by astronomer Alexander Kashlinsky, suggest that galaxy clusters, which are vast collections of galaxies bound together by gravity, are moving in a specific direction beyond what can be explained by the known gravitational influences of nearby matter. This peculiar motion hints at a force or influence from regions of the universe that are not visible to us, leading to the term dark flow. When much of the universe's mass exists, dark matter does not emit, absorb, or reflect light, making it incredibly elusive. It is believed to make up about 27% of the universe's total mass, energy content, and it plays a pivotal role in the structure and formation of galaxies. The idea of dark flow suggests that there may be large-scale structures or gravitational influences beyond our observable universe that could be affecting the motion of these galaxy clusters. If dark flow is indeed real, it could imply that there are vast regions of dark matter exerting gravitational pull, which could help explain why these clusters are moving in such a coordinated way. On the other hand, dark energy, which is thought to make up approximately 68% of the universe, is even more enigmatic. It is the driving force behind the accelerated expansion of the universe. The relationship between dark flow and dark energy is less direct, but it raises intriguing questions. If dark flow indicates the presence of unseen mass, could it also suggest that there are areas of dark energy influencing these movements? The interplay between dark matter and dark energy is still a subject of intense research, with scientists trying to unravel how these components shape the universe's fate. Moreover, the implications of dark flow could extend our understanding. If these galaxy clusters are moving towards a specific region, it may point to the existence of a larger cosmic structure, perhaps even hinting at the possibility of an unseen universe beyond our own. This aligns with some theories in cosmology, which suggest that our observable universe is just one of many, potentially connected through vast cosmic webs of dark matter and energy. As researchers continue to study the universe, the mysteries surrounding dark flow, dark matter, and the existence of dark flow, a mysterious phenomenon where galaxy clusters appear to be moving in a specific direction, raises intriguing philosophical questions about our universe and challenges our perception of reality, as well as the nature of cosmic structures. Dark flow suggests that there may be influences beyond our observable universe, hinting at the possibility of structures or forces that we have yet to comprehend. And this leads us to ponder the limitations of human knowledge and the extent of the universe itself. If dark flow is indeed caused by gravitational forces from regions beyond our observable universe, it implies that our current understanding of the cosmos might be incomplete, and this notion can be unsettling, as it confronts the idea that we are not the center of everything, but perhaps a small part of a much larger, interconnected cosmic system. Moreover, the philosophical implications extend to the nature of reality and existence. If there are aspects of the universe that we cannot observe or measure, it challenges the very foundation of empirical science, which relies on observation and experimentation. This leads to questions about the nature of truth in science, as well as the epistemological boundaries of human understanding. Can we ever truly know the universe if there are phenomena occurring outside our observational reach? Such considerations can lead to a more humble perspective towards our pursuit of knowledge, acknowledging that there may always be elements of the universe that elude our grasp, prompting us to develop a sense of wonder and curiosity, rather than certainty. Furthermore, dark flow could suggest that the universe is not just a random collection of matter and energy, but rather a complex, interconnected web of forces and influences, which could have implications for our understanding of causality and interconnectedness on a cosmic scale. This perspective aligns with philosophical ideas that emphasize the unity of the cosmos encouraging a holistic view of the universe where everything is linked and every action has far-reaching consequences, thus pushing us to consider our place within this grand scheme and what responsibilities we might have towards understanding and protecting our universe. Lastly, the existence of dark flow may also inspire deeper reflections on the human condition as we grapple with the vastness of the cosmos and our seemingly insignificant position. This realization can evoke both awe and existential contemplation, prompting us to question our purpose and significance in such an expansive universe. Should we see ourselves as mere observers, or do we play a role in a larger narrative that we are yet to fully comprehend? These questions, fueled by the mysteries, dark flow is a fascinating phenomenon in cosmology, and it has the potential to provide insights into the early universe, as well as the conditions that existed shortly after the Big Bang. To understand how dark flow might inform us about these early conditions, we first need to grasp what dark flow actually is. Essentially, dark flow refers to the peculiar motion of galaxy clusters that appears to be moving in a specific direction, beyond what can be accounted for by the known gravitational influences of nearby matter. This movement suggests that there may be some unseen structures, or perhaps vast regions of matter, that are exerting gravitational forces on these galaxy clusters, pulling them in a certain direction. The discovery of dark flow raises intriguing questions about the distribution of matter in the universe and the influence of gravitational forces on large scales. If dark flow is indeed caused by gravitational pulls from structures beyond the observable universe, it could hint at the existence of vast superclusters or even other forms of mass that we have yet to identify. This has implications for our understanding of the early universe, as it suggests that the universe may have been influenced by large-scale structures much earlier than we previously thought. In the moments following the Big Bang, the universe was a hot, dense state, and as it expanded, the distribution of matter and energy began to evolve. The presence of dark flow implies that even in this early phase, there may have been gravitational interactions that shaped the large-scale structure of the universe. Moreover, studying dark flow might help us understand the cosmic microwave background radiation, which is the afterglow of the Big Bang, providing a snapshot of the early universe. The patterns we observe in the cosmic microwave background could be influenced by the gravitational effects of these unseen structures that dark flow hints at. If dark flow aligns with certain patterns in the cosmic microwave background, it could validate theories about the early universe's expansion and the conditions that prevailed during that formative period. Furthermore, dark flow could also shed light on the concept of dark energy, which is thought to be driving the accelerated expansion of the universe. Understanding how dark flow interacts with the overall dynamics of cosmic expansion could provide clues about the role of dark energy in the universe's structure and evolution. If dark flow is linked to areas of high density or mass, it could suggest that dark energy behaves differently in those regions, affecting the rate at which galaxies and clusters are moving away from each other. In conclusion, dark flow serves as a window into the dynamics of the early universe. Dark flow is a fascinating phenomenon that has intrigued cosmologists since it was first observed in the early 2000s. It refers to a peculiar motion of galaxy clusters that seems to be moving in a specific direction, away from the expected patterns influenced by the cosmic microwave background radiation, which is a remnant of the Big Bang. This motion suggests that these clusters are being pulled by some unseen force, leading scientists to hypothesize about the existence of structures beyond our observable universe. The implications of dark flow for the fate of the universe are profound and complex, opening up a range of possibilities that challenge our current understanding of cosmology. If dark flow is indeed the result of gravitational influences from a massive structure outside our observable universe, this could imply that our universe is part of a larger cosmic tapestry, one that includes regions we cannot currently see or measure. This notion raises questions about the overall geometry and topology of the universe, suggesting that it might not be as uniform as we once thought. As a result, the fate of our universe could be influenced by these unseen structures, potentially altering our understanding of cosmic expansion and the ultimate destiny of galaxies. Moreover, dark flow could provide insights into the nature of dark energy, which is believed to be responsible for the accelerated expansion of the universe. If dark flow indicates the presence of substantial mass outside our observable horizon, it might suggest that dark energy behaves differently than we currently understand, leading to a reconsideration of the forces at play in cosmic evolution. This might also affect predictions about the long-term fate of the universe, such as whether it will continue expanding indefinitely, reach a stable state, or eventually collapse. Additionally, the existence of dark flow could hint at the possibility of multiple universes or a multiverse scenario. If our universe is influenced by the gravitational effects of other unseen universes, this could fundamentally change our understanding of reality itself. The implications of this idea stretch beyond the physical properties of space and time, raising philosophical questions about the nature of existence and our place within a potentially vast and varied cosmos. Investigating dark flow also challenges the limits of our observational capabilities. If these galaxy clusters are indeed moving in a direction we cannot fully comprehend, it could necessitate new methods and technologies to study the universe, pushing the boundaries of astronomy and physics. Observations of dark flow may lead to a deeper understanding of cosmic structures and their evolution over time, potentially reshaping our models of the universe's past, present, and future. In conclusion, the